welcome to this explainer. Today, we're unpacking an absolute classic, a completely open-ended coding problem that's practically a rite of passage in technical interviews. We're talking about sorting an array.
So, let's just dive right into it. It sounds incredibly simple, right? You just take a jumbled list of numbers and, well, put them in ascending order. But what actually happens when the interviewer says you can't just use a built-in sort function? Suddenly, you're building the engine totally from scratch, and the algorithm you choose, it can literally make or break your code's efficiency.
Here's our quick roadmap for today. We'll cover the sorting problem, conquering with quicksort, the partitioning process, avoiding the worst case, and finally, a fun interview curveball.
Section 1. The sorting problem. Like I said, sorting seems simple, but every single algorithm comes with its own unique pros and cons depending on your specific constraints. For the first part of this explainer, we're going to focus on a real heavy hitter, quicksort. It's this brilliant divide-and-conquer strategy. Conceptually, it sorts an array by picking just one number, which we call the pivot, and placing it perfectly in its final sorted position at each step. You can kind of think of the pivot like a strict room divider. We take our pivot, in this case the number 5, and we literally just throw everything smaller than 5 to the left side and everything larger to the right. Now notice the left and right sides aren't actually sorted yet, but that 5, it's locked in perfectly. Then we just recursively apply that exact same strategy to the left and right chunks.
Section 2. Conquering with quicksort. Let's see how we actually arrange those numbers around the pivot in real, efficient code.
The real secret sauce here is executing this partitioning step in linear time without eating up extra memory. We do this by setting up two simple pointers. First, we pick the rightmost number, 5, as our pivot. Then, we drop a pointer called low at the start of the array to track exactly where the next small number should go. Our second pointer, I, acts as our active scanner. All right, so as pointer I begins scanning from left to right, it's hunting for just one thing, numbers smaller than our pivot, 5. The first number it looks at is 6. Well, 6 is bigger than 5, so I kind of just shrugs and keeps moving right. Next up, I hits the number 8. Again, 8 is bigger than 5, so the scanning pointer just skips ahead. And during all of this, notice that our low pointer hasn't moved an inch. It's just patiently waiting for a small number.
Aha! Our scanner I finally hits the number 4. And since 4 is definitely less than our pivot 5, this triggers our next crucial action.
Here's the magic. We immediately swap this newly found smaller number, 4, with whatever number is currently sitting at our low pointer. The 4 and the 6 instantly trade places, and bam! The 4 is now safely tucked on the left side of the array. Since we successfully placed a small number at the low index, we just bump that low pointer up by exactly one space. Now it's pointing at the 8, standing by, completely ready to receive the very next small number our scanner I happens to stumble across. From here, we just repeat this snappy, rhythmic process. The scanner I finds the 2, we swap it to the low pointer and increment low. It finds the 3, swap it, increment. Finds the 1, swap, increment. You get the idea. We do this until I has evaluated every single number right up to the pivot. And for the grand finale of the partition process, all the small numbers are packed on the left. The low pointer is currently sitting on the first large number, which in this case is 8. So we do one final swap. We trade our pivot, the 5, with the number at the low pointer. Boom. The 5 is now perfectly sorted right in the middle, dividing the smalls and the bigs. Moving to Section 4, avoiding the worst case. Now, what's really interesting here is a fatal flaw hidden within the quicksort partitioning we literally just walked through, and we absolutely need to fix it if we want to code like pros. Look, on average, quicksort is blazing fast. We're talking O of n log n time. It divides the array roughly in half every single time, keeping the recursion nice and shallow. But in the absolute worst-case scenario, this algorithm can drastically slow down to a super sluggish O of n squared. Just think about why this bottleneck actually happens. Imagine if the array was already sorted, right? And we blindly picked the rightmost element as our pivot. Because it's already the largest number, there's absolutely nothing to put on its right side. We end up creating these wildly unbalanced partitions, where one side has all the remaining numbers and the other has 0. That forces our code into a really deep, highly inefficient recursive spiral. Luckily, the fix is elegantly simple. We can dodge this worst-case scenario by introducing just a tiny bit of chaos. Instead of always picking the rightmost number as our pivot, we simply pick a completely random index in our chunk and swap it with the rightmost element right before we start partitioning.
This one single optimization breaks the dependency on the array's initial order, virtually eliminating the worst-case scenario. It's a total game changer.
Section 5. The interview curveball. Okay, let's say you've just perfectly coded this optimized quicksort, and your interviewer leans back, smiles, and throws a curveball to put you right back in the hot seat. They say to you, okay, assume the array has absolutely no negative numbers and the highest value possible is only 1,000. Then they ask, should we still use quicksort?
Actually, no. When your data range is this small and well-defined, we can completely shift gears to a totally different non-comparison-based algorithm called counting sort. And it works in two incredibly straightforward steps. First, we just count how many times each number appears. Second, we use those counts to literally build our final sorted array.
Since our maximum possible value is only 1,000, we basically just create a tally sheet, a counts array. We walk through our input exactly once, putting a tally mark next to each number we see. 2 zeros, tally them up. 3 twos, tally them up. Then we just print out the tallies in order. We completely bypass the need to ever compare two elements against each other, meaning this runs in an incredibly fast O of n plus k time.
But hey, don't throw away quicksort just yet. You always have to remember why you pick an algorithm. See, counting sort requires you to build an entirely new counts array in memory. If your max number was, say, 1 billion, you need a massive amount of memory for that array. Quicksort, on the other hand, is an in-place sorting algorithm. Aside from some recursive stack space, it doesn't need massive extra memory arrays to get the job done.
Hopefully, this explainer gave you the confidence to ace an open-ended sorting question and really deeply understand the mechanics behind the code. So I gotta ask, next time you just casually type .sort in your codebase, will you actually know what's happening under the hood? Keep exploring, keep optimizing, and I'll catch you in the next explainer.